Fire and gas system, modernized design, and functional strategy. The Fire and Gas System FGS is a critical life safety and asset protection layer in industrial environments designed to detect and respond to the presence of fire, combustible gases, and toxic gases such as H2S. In modern facilities, FGS is fully digital, cyber hardened, and SIL 23 compliant, integrated within the Distributed Control and Safety System DCSS architecture while maintaining operational independence and fail-safe characteristics. Core objectives and protection philosophy. Continuous hazard detection. The FGS autonomously monitors production, utility, and accommodation areas for early signs of combustion, gas leaks, or toxic release. Initiates alerting, suppression, and interlocked emergency shutdown functions as defined in the Fire and Gas Cause and Effect Matrix. Automatic protective actions. Upon verified detection, the FGS triggers outputs for local alarms, beacons, sounders, initiates ESD interlocks, activates firewater systems, starts ventilation shutdowns, and commands process isolation and depressurization. Personnel alerting and evacuation readiness. The system interfaces with public address and general alarm PAG-A systems to broadcast evacuation signals, pre-recorded instructions, and muster zone updates. Integration with access control and people counting systems supports safe and coordinated evacuations. Architecture and 3 certified safety controllers. The FGS runs on a high reliability to be certified PLC or Safety Instrumented System SIS with TMR or 102D redundancy. All control logic is deterministic, real-time, and independently executed from the DCS. High-density Smart I/O. Smart I/O modules with built-in diagnostics support digital and analog detectors, including flame, heat, smoke, IR/UV, H2S, and LLUEL gas detectors. Input loops are continuously monitored for open circuit, short circuit, and drift. Dual redundant communication and power. FGS architecture includes redundant power supplies, dual communication links, and fiber optic backbone integration to ensure system availability even under cable fault or partial system damage. System segregation and cybersecurity. FGS is isolated in a secure safety zone per ISA IEC 62443. Communications to other systems, DCS, PEGA, HVAC, are mediated via secure protocol gateways or safety field bus, e.g. ProfiSafe, ASI safety. Detection infrastructure, multi-layered detector types, hydrocarbon gas detectors, point and open path infrared, toxic gas detectors, e.g. H2S electrochemical cells, UV IR and triple IR flame detectors, rate of rise and fixed temperature heat detectors, addressable smoke detectors for enclosed and HVC areas, manual call points with location-specific LED feedback. Detector placement optimization. Smart 3D modeling and computational fluid dynamics (CFD) simulations are used to determine optimal detector placement, taking into account wind patterns, gas dispersion, and flame visibility. Voting logic and zone isolation. 2N voting is applied where required to eliminate false positives. Detection zones are configured for independent control of fire suppression, ventilation isolation, and shutdown command propagation. System outputs and actuation. Hardwired fail-safe outputs. FGS outputs for critical actions, e.g. deluge actuation, damper closure, ESD interlocks, are hardwired directly to the actuating elements. All outputs are designed to de-energize to trip state under failure or detection. Pulse-tested field devices. Outputs to actuators are pulse-tested for coil integrity, wiring continuity, and load resistance. Results are logged and trigger maintenance alerts upon fault detection. Extinguishing system integration. FGS interfaces directly with deluge valves, gas suppression panels, e.g. FM200, Novec, and foam systems. Activation and status feedback loops are monitored for execution confirmation. Operator interface and visualization. Unified operator display. FGS status, detection points, overrides, and fault diagnostics are presented on DCS and dedicated mimic panels. Graphical overlays show fire zones, detector types, active alerts, and suppression actions in real time. Zone-wise mimic panels. Physical LED-based mimic panels present clear visual status of detection zones and system state. LEDs are color-coded by hazard type, e.g. gas, fire, fault, and grouped by plant area for rapid situational awareness. Real-time notifications and guidance. The interface provides guided response steps during active detections, including immediate safety actions, system lockout status, and visualized cause and effect tracebacks. Overrides, maintenance, and diagnostics. Controlled maintenance override functions. Individual detector inputs can be overridden for maintenance under a dual authority protocol. Overrides are initiated via secure workstation interface, enabled through hardwired maintenance toggle switches, MOAS, and flagged via alerts and HMI indication. No output overrides permitted. Outputs tied to suppression systems, shutdown actions, or life safety responses cannot be overridden. Any attempt or system fault forces a visible alarm on the console and MIMIC panel. Predictive diagnostics and fault isolation. Smart detectors provide sensor aging, contamination, calibration drift, and fault data. Predictive analytics identify degradation before functional loss, allowing scheduled maintenance instead of reactive replacement. Testing and compliance. Automated system health monitoring. System diagnostics continuously monitor every detection loop, output driver, communication bus, and power supply. Faults are localized and displayed with timestamp and module device identification. Digital proof testing and simulation. Proof tests are digitally executed using software simulators and loop testers with automatic result capture and compliance logging. Full system simulations support virtual FAT-SAT and emergency drill exercises. Standards adherence. The system is fully compliant with IEC 61508, IEC 61511, NFPA 72, and local fire codes. All functional safety documentation is maintained digitally through lifecycle management tools, supporting audits and insurance reviews. Remote and cloud integration. Cloud-based event archiving and analytics. All events, test records, and fault logs are mirrored to secure cloud repositories for long-term analysis and KPI tracking. Dashboards can be accessed by fire safety teams, plant managers, and corporate HSE. AR-assisted field maintenance. Technicians can use augmented reality glasses to receive guided steps for detector calibration, fault isolation, and device replacement, with real-time data from the FGS streamed into their view. Modern fire and gas systems transform reactive hazard detection into a proactive safety framework. With intelligent diagnostics, autonomous actuation, and integrated emergency coordination, the FGS becomes not just a safety system, but a real-time guardian of personnel, plant, and production continuity. Fire and gas design guidelines, modernized framework for high-integrity safety systems. Designing a contemporary fire and gas system, FGS, requires a precise balance of detection sensitivity, system resilience, cyber hardening, and operational clarity. The following guidelines reflect the latest global best practices and technological standards for implementing a high-integrity FGS that complies with IEC 61550/61511, NFPA, and industry-specific safety philosophies. Detection system design, multi-sensor, multi-technology detection strategy. Deploy a layered detection network using diverse technologies, e.g. UV-IR, triple IR, point and open path gas detectors, smoke, heat, and flame sensors. Detector types are selected based on hazard potential, environmental factors, and response time requirements. Smart, addressable detectors with built-in diagnostics. All detectors shall support continuous self-checks and report calibration drift, contamination, line integrity, and aging metrics via digital protocols such as HART, Foundation Field Bus, or Modbus. Non-smart, passive detectors are discouraged except in low criticality zones. Optimized detector placement using CFD modeling. Fire and gas detector coverage is designed using computational fluid dynamics (CFD) simulations, considering wind patterns, enclosure ventilation, density gradients, and potential leak sources. Coverage maps are validated during design and verified during commissioning. Voting logic for fault tolerance and nuisance rejection. Apply 1.1.2 or 2.0.3 logic configurations where false positives are likely, especially for open path or IR flame detectors exposed to environmental noise. Voting schemes are dynamically visualized for operator transparency, signal integrity, and loop supervision. Continuous line monitoring for all inputs. Every detection loop includes line supervision for short circuit, open circuit, and earth leakage faults. Loop integrity monitoring is performed in real time, and all faults are reported as maintenance alarms. Pulse-tested and monitored output circuits. All actuator outputs, deluge valves, fire dampers, solenoids, audible visual alarms are pulse-tested for load health and integrity. Output status is verified through dual feedback mechanisms, typically current sensing and discrete position switches. Power source control and isolation. All detector and output loop power is supplied by the FGS system itself, with isolated power domains for redundancy and safety separation. Power feeds are individually fused and monitored for voltage stability, ground fault, and overcurrent conditions. System configuration and logic. Modular, IEC 61508 certified safety PLC architecture. FGS logic shall run on a CL23 rated PLC or SIS, modularly scalable and physically segregated from non-safety systems. The system supports deterministic scan cycles and redundant execution paths, 102D or TMR as applicable. Digital cause and effect matrix integration. The fire and gas logic is configured using a graphical cause and effect matrix engine. Any change in logic auto-generates documentation updates and must pass simulation tests before deployment. All C&E data is traceable and version controlled. No addressable detection in open plant areas. For outdoor and process critical areas, conventional, non-addressable loops are mandated due to their deterministic response time and fault isolation. Addressable detection is limited to enclosed, non-hazardous environments, e.g. control rooms, LQ. Maintenance and overrides. Individual input maintenance override. Each detector input has its own override capability initiated via secure workstation action and enabled through a hardwired maintenance override switch, grouped by zone or device type. Overrides disable only the specific logic element, not the physical detection signal or its display. Override indication and alarming. Activation of any override must illuminate a yellow backlit indicator on the FGS Mimic or operator console, generate a workstation notification, and print an event log. Overrides are time-limited and must be manually cleared. No output overrides allowed. Under no circumstance is output override, e.g. suppression actuation or trip signals, permitted. Safety actions are considered irrevocable unless reset through formal clearance protocols and logic permissives. System visualization and operator interface. Live interactive fire and gas mimics. Operator consoles display live plant layouts overlaid with detection zones, real-time sensor status, active alarms, and logic state. Mimics must distinguish between fault, alert, override, and active hazard through clear color coding and iconography. Event logging and diagnostics. All events, including detection signals, logic transitions, overrides, faults, and resets, are time-stamped and stored in a secure sequence of events SOE recorder with millisecond resolution. Operator actions are also logged with user ID for audit compliance. Mobile and remote diagnostics. Maintenance staff may access FGS diagnostics and health status via encrypted tablets or AR headsets, enabling on-the-spot fault isolation and guided troubleshooting with digital overlays. System output design and response strategy. Default to de-energize to trip philosophy. All field outputs are fail-safe, de-energized to activate safety action. Actuators, e.g. dampers, solenoids, revert to their safe position on loss of signal, power, or FGS system integrity. Zoned actuation logic. Outputs are grouped and assigned to specific fire gas zones, allowing localized response, e.g. gas suppression in one module, deluge in another, without unnecessarily tripping unaffected systems. Dual-channel output verification. Outputs for critical systems include dual-channel confirmation. Both command signal and end-device feedback are required to validate actuation. Failure of either path raises a safety-critical maintenance alarm. Compliance, testing, and lifecycle support. Functional safety verification and audits. Every FGS design must pass formal safety reviews, e.g. SIL verification, LOPA, C&E validation, and be documented within a safety lifecycle management system. All logic, architecture, and proof tests must align with IEC 61511/61508. Digital proof testing and reporting. Proof tests are conducted via simulation, manual activation, or partial stroke testing of actuators. Results are auto-logged, time-stamped, and included in audit trails. Missed or overdue proof tests trigger alerts and maintenance workflows. Lifecycle maintenance integration. The FGS must interface with the CMMS, e.g. SAP PM Maximo, to trigger maintenance work orders based on diagnostics, proof for performance degradation trends. Modern fire and gas system design must not only detect hazards quickly, but also manage data, diagnostics, and decisions intelligently. These guidelines ensure a robust, transparent, and operator focused implementation that transforms the FGS from a passive alarm system into a proactive, predictive safety infrastructure. Management Information System, modernized integration for distributed control systems. The Management Information System, in a contemporary distributed control system (DCS) architecture, serves as the intelligent data layer that connects real time process operations with enterprise level decision making. No longer just a reporting tool, the modern MIS provides high frequency data aggregation, advanced analytics, and secure visualization across production, maintenance, safety, and energy domains, driving actionable intelligence at all organizational levels. System objectives and role, real time operational visibility. The MIS provides continuous, centralized access to plant performance indicators, process trends, equipment health, and alarm event logs. This enables control room operators, engineers, and corporate stakeholders to monitor operations securely from any authorized location. Data-driven decision support. By converting raw DCS data into contextualized insights, the MIS supports predictive maintenance, production optimization, energy efficiency tracking, and compliance reporting. It functions as the bridge between OT, operations technology, and IT, information technology, domains. Enterprise Integration Layer. MIS seamlessly connects DCS data with ERP, e.g. SAP, CMMS, e.g. Maximo, MES, LIMS, and cloud analytics platforms. This integration enables synchronized scheduling, inventory tracking, batch genealogy, emissions monitoring, and audit compliance. Technical architecture and infrastructure. Industrial data lake architecture. A hybrid architecture combines edge historians, on-premise time series databases, and cloud-based storage, e.g. Azure IoT, AWS IoT Sitewise. Real-time data flows through secure brokers, e.g. OPC UA PubSub MQTT, Sparkplug B, into high-availability clusters designed for redundancy and scale. Unified namespace model. All plant assets, tags, and data streams are organized under a structured namespace, enabling consistent data access across dashboards, analytics models, and digital twins. Semantic models are built using ISA 95 or IEC 6264 standards. Scalable data processing. Stream processing engines, e.g. Apache Kafka, Azure Stream Analytics, manage high-volume, low-latency data for KPI generation, condition monitoring, and event correlation. The system supports distributed analytics deployment across edge and cloud. Key functional capabilities. Real-time dashboards and KPIs. Web-based dashboards provide live displays of production rates, energy consumption, OEE, overall equipment effectiveness, emissions, safety system status, and equipment downtime. Dashboards are customizable by role and accessible via desktop, tablet, or mobile. Advanced reporting and visualization. Interactive reports are created using tools such as Power BI, Tableau, or Grafana. Reports support drill downs by plant area, shift, or equipment group and can be scheduled hourly, daily, shift-wise, or executed on demand. Output formats include PDF, Excel, HTML, and cloud share links. Alarm and event analytics. MIS aggregates DCS, ESD, and FGS alarm logs, enabling analysis of nuisance alarms, standing alarms, and alarm floods. It supports KPI tracking such as alarms per hour, operator response time, and top 10 frequent tags. Predictive maintenance integration. Asset health data from smart sensors, vibration monitors, and motor analytics is ingested to compute remaining useful life, RUL, MTBF, and condition indexes. Predictive models notify stakeholders before failures occur, triggering automated CMMS work orders. Production and efficiency tracking. MIS calculates mass balances, energy KPIs, yield losses, and downtime across process units. It compares targets to actuals, provides alerts for deviation, and supports root cause identification. Cybersecurity and access control. Zero trust architecture. All MIA connections are authenticated and encrypted. TLS SSL with role-based access control, RBAC, and multi-factor authentication, MFA. User activity is logged for compliance. Secure remote access. Authorized users such as plant managers, process engineers, and corporate HSE can access MIS dashboards from offsite locations via VPN, web portal, or mobile app. Data replication ensures no live control data is exposed externally. Network segmentation and DMZ integration. MIS operates in a demilitarized zone, DMZ, between the DCS and corporate networks, using unidirectional gateways, data diodes, or firewall-managed bidirectional interfaces. This isolates control systems from cyber threats while enabling safe data flow. Interoperability and API ecosystem, RESTful and OPC UA APIs. Open APIs allow MIS data to be accessed by business applications, cloud analytics, or third-party dashboards. Secure endpoints support JSON XML formats, tokenized access, and audit logging. Plug-and-play IoT integration. MIS supports the onboarding of IoT devices and edge analytics gateways using protocols like MQTT, LoRaWAN, and OPC UAFX. This expands coverage to rotating equipment, standalone skids, and non-DCS assets. Lifecycle and data governance, automated data archival. MIS archives raw and aggregated data into structured repositories with retention periods defined by regulation, e.g., 3, 5, or 10 years. Storage includes auto-tiering from fast SSD to low-cost object storage. Audit and compliance logging. All user access, report generation, system changes, and data exports are logged with timestamps, user IDs, and access methods. Reports are available for ISO 9001, ISO 27001, and industry-specific compliance audits. High availability and disaster recovery. MIS operates in a clustered, failover-ready architecture with redundant database servers, mirrored storage, and automatic failback. Cloud replication ensures disaster recovery in minutes with minimal data loss. Advanced extensions, AI-driven anomaly detection. MIS integrates AI ML models trained on historical operations to identify early warning patterns. These models generate risk scores and recommend preventive actions in collaboration with operators. Digital twin synchronization. Real-time DCS and MIS data feed into physics-based or data-driven digital twins for pumps, compressors, reactors, and utilities. This enables simulation of process changes like what-if scenarios and virtual commissioning. Sustainability and ESG reporting, environmental data, e.g., flare volumes, GHG emissions, water usage, is aggregated and aligned to corporate ESG goals. Dashboards support Scope 1/2-3 tracking and automated reporting to sustainability frameworks, e.g., GRI CDP. The modern MIS is no longer a passive observer. It is a real-time, predictive, and strategic intelligence layer that transforms operational data into business value. Whether optimizing uptime, reducing emissions, or enabling remote operations, the MIS is the digital backbone that empowers resilient, data-driven industrial performance.